Okay, so here is a video of me going through basically the homework assignment I've given you over this break here for sections 3.1 to 3.5 because there are obviously some gaps we have somewhere that we need to get cleared up. So the first one we're going to start with is these sketching functions problems. They give us all the stuff we have to find. You've got to find domain, zeros, y-intercept, coordinates of the extrema, intervals where it's increasing, decreasing, coordinates of the inflection points, intervals where the function is concave up, concave down, and then actually sketch the graph of the function. Now the only two I'm making you do those for are 724 and 726, but on 725 and 727 I want you to find the inflection points and sorry, I had to fix something on here. I just realized I have to reprint this tomorrow. Dang it. The rest you're going to do for just the extrema and inflection points. So, first of all, number 724. Okay. So the function is h of x equals x minus 1, the quantity cubed, times x minus 5. Now, some of you may be tempted to expand that out. The problem with expanding this is that it doesn't, it becomes a quartic and it's kind of a pain to factor. So really when you're going to do this, you're going to want to use the product rule. Now, domain-wise, okay, this is a polynomial, so domain's all reals. The zeros, set this guy equal to 0. It's already factored for us. So our two zeros are going to be at x equals 1 and 5. Y-intercept, that's when x equals 0, so plug 0 in for x. You get negative 1 cubed times negative 5. That's going to be positive 5. Because the negative 1 cubed is going to be negative 1 times negative 5 will be positive 5. And now we start finding our extrema. Okay, so really, for some of you, what your biggest issue is, there's two issues you have. Okay, one, you don't know what, you know what to do and how to do it, you just don't know when to do what to do. Okay, so first derivative gives us the extrema. It gives us the max and mins. It tells us if we're increasing or decreasing, and we're looking for is when the first derivative equals 0. Now this is polynomial, so it's also it's even-powered polynomial because it's 3 and 1, so this should look something with like even in behavior like this. Something in the middle is going to happen weird. We don't know what. It might go up and down or whatever, but it's got to be ended like this. But either way, I don't have horizontal asymptotes. I don't have vertical tangents. I just have a polynomial. So when I do h prime of x, okay, I'm going to do the product rule. So the derivative of the first group is bring this. I treat this as the first group. This is the second group. Bring the 3 to the front. Leave the inside alone. Subtract 1 from the power, and then multiply by the derivative of the inside, which is just simply 1. Leave the outside, and then leave the other one alone. Then add the other part. We'll leave the x plus x minus 1 alone, and then take the derivative of the other one, which is just simply 1. Okay. Now, I'm going to simplify this just a touch, just because of the fact that I want to just kind of, I want to have it as simplified as possible before I start factoring things out. And the 1 times 3 is that, and this is just x minus 1 cubed. Because that's also part of the problem is the algebra for some of you. Your algebra skills are deficient. I don't mean that in any way, just they are. You don't have the algebra background to do some of this work. So I'm going to factor out, but the lowest I have is 2 of these guys here. So this is really x minus 1, the quantity squared, times another x minus 1 if I split this. So I'm going to take both of these out. X minus 1 squared leaves me with 3 times x minus 5 plus x minus 1. Okay. And then I can simplify this inside as 3x minus 15 plus x minus 1. I get 4x minus 16. Okay. And then even that I can factor a bit further. I can take a 4 out. So I have 4 times x minus 1 squared times x minus 4. That gives me then 2 zeros of 1 and 4 for my extrema. Again, I'm looking for the first derivative equaling 0. That happens twice. x equals 1, and x equals 4. Okay. Now, before I can determine if this is a max or a min, though, I have to do my first derivative test on the number line to see if I'm going to have increasing or decreasing behavior. So one of the nice things is no matter what I plug in for x minus 1, I'm going to square it, so it's going to become positive. So the real question is, what happens for x minus 4? Well, if I plug a number in left of 1, that's negative. Number between 1 and 4, that's negative. Number after 4, that's positive. So again, just plugging numbers in to this first derivative to see if this is positive or negative on the number line. Well, now I see that it's really all it's going to happen at 1 is it's going to be a horizontal tangent, which is important to know. So horizontal tangent. But negative at 4, that's a minimum. Okay. So now I can figure out what that minimum actually is by plugging 4 into the original function. I can find h of 4. Well, that's 4 minus 1 cubed, so that's 3 times 3 times 3, so it's 27, times 4 minus 1, which is negative 1. So h of 4 is negative 27. So I have a min of negative 27 at x equals 4. And hopefully you're not watching this on your phone. I did this in pen instead of my marker because I wanted it to be a little more condensed. I also have that behavior-wise it is decreasing from negative infinity to 4. Even though there's a brief moment of the horizontal, it's not. We're not going to consider that anything because it's just for one moment. And then it's increasing for 4 to infinity. Okay. So this is actually the extrema here is part D. Increasing, decreasing is part E. Now I get to have the fun of starting all over again and doing the second derivative business for part F. Concavity and rules. So here's the deal. I'm going to take actually this derivative here, not this one with the 4 factored out because I have to deal with that 4 as an extra term. So I'm just going to do this one here and do the product rule again. H double prime of x. Derivative of x minus 1 is 2 times x minus 1 to the first. Derivative of the inside is 1. Then times 4x minus 16. Plus, leave the first one alone, x minus 1 squared. Times the derivative of the inside, which is 4. Okay. And then I can simplify that a little bit. It'll be 2 times x minus 1 times 4x minus 16 plus 4 times x minus 1 times x minus 1. And the reason I'm writing that x minus 1 twice now is so I can remind myself that, oh yeah, I'm going to take out an x minus 1. In fact, if I wanted to, I could even take another 4 out because this is really here 4 times x minus 4. So I'll take out the 4 as well. And what that's going to leave me with then is for h double prime of x, 4 times x minus 1. Left over will be 2 times x minus 4 plus 4 times x minus 1. Okay. If I simplify this as 2x minus 8 plus 4x minus 4, what that gives me then is 4 times x minus 1 times 6x minus 12, which I can take out a 6 here even. Let's see how good it's on the screen. Take out the 6, that gives me 6 times x minus 2. So I really have 24 times x minus 1 times x minus 2. Okay, so my zeros in for my inflection points are going to be 1 and 1 and 2. So let's test it on that second derivative number line. Okay. Now, this time I really just have to concern the 24 is positive, so I kind of ignore it. So the question is, what happens left of negative left of 1? Like with 0, that gives me negative 1 times negative 2. That's positive. Here is going to be negative. Here is going to be positive. So I know I have concave up from negative infinity to 1, and then from 2 to infinity. And then I have concave down from 1 to 2. And, more importantly, this is an inflection point at x equals 1. So it's going to be, my inflection points are 1, 0, because I already know that 1 made it 0 to begin with up here when I plugged 1 in. 1 minus 1 was 0 times negative 4. And then when I plug 2 in, 2 minus 1 is 1. 2 minus 5 is negative 3. So it's going to be at 2, negative 3. Okay. So I have all this information. That's all the data I'm supposed to do. Now I have to graph this. So I'm going to move this off to the side. Get out my xy axis. Okay. I don't have a ruler at home, do I? Nope. Dang it. I did have one, but my daughter stole it. Now, one thing I will say is that our min is pretty darn extreme. Okay, so for my numbers, I'm going to go by threes. Okay, my x I'll just go by ones. So I had a 0 at 1. I also had a 0 at 5. Okay, at 0 I actually had a y-intercept of positive 5. So this is 3, this is 6. So it's somewhere like that. Okay, so I had that. Now those points, and then my minimum was at 4, negative 27. Okay, at a minimum of 4, negative 27, so over 1, 2, 3, 4 down to negative 27 here. Okay, and then my inflection points were again 1, 0, and 2, negative 3. So over 2, down 3. It's right here. Now, increasing from, let's see here, it was from 4 to infinity, decreasing from negative infinity to 4. So I'm going downwards from here, and then I go back up. And then my concave up from negative infinity to 1, I think, is what it was. No, so yeah, to 1. Concave down from 1 to 2, and then concave up again from 1 to infinity. So we have to go, basically come through here, concave up. Now it is a brief horizontal tangent, but that's also where the concavity switches to concave down, is there. And then it switches back to concave up again, and kind of goes up through there. So yeah, I'm kind of, ugh. That's why you don't use a pen, so you can erase stuff, but pen does not show up on my document camera. So there we go. That's graph. Now, if you look at your timer, like 12 minutes and 15 seconds. That's a fair amount of time to take for this, but I really did go slowly. There was a lot of algebra to sort out, but I bet for some of you, you don't take 12 minutes to do a problem like this in your homework. Okay, and that's part of the problem, is then when you come to test time, it takes you much longer to do it than it should. Now, number 725. Okay, I said extrema and inflection points. So we don't have to do the so 725 is f of x equals x minus 2 to the 1/3 minus 4. Now we're not going to graph this because what happens is the points for this kind of get insane. But we do need to know domain anytime we do extrema and inflection points. And this is a cube root function, so this domain's all reals. So now we go to do our extrema. That takes the first derivative for us. 1/3 drops into the front, x minus 2. Negative 2/3 for the power then when I subtract 1 from the exponent, and that is a negative 2/3, sorry. And then the derivative of the inside's 1. And then the negative 4, its derivative is nothing, it's 0. So I could say plus 0. Or more importantly, it just drops off. Okay. So f prime of x is then, if I really rewrite this, 1 on top over 3 times x minus 2 to the 2/3 power. Now, what's important about this is I can't make this equal 0 because 1 on top will never be 0. Now that's a fraction. However, I will have a number at x equals 2 as a critical number because it makes the denominator equal 0, which makes it undefined. So we have a critical number of x equals 2. And you might say, well, I can't do undefined. Yes, I can, because 2 is in the domain to begin with, because everything was in the domain. What that really means is we have I think if I remember correctly with this one, it's a cube root graph, but we actually have a vertical tangent for a brief moment. So take out my number line. 2 is my number to check. It's undefined there. And the nice thing is this. I'm going to plug a number in for this. Well, this is going to be to the 2/3 power. So you're going to take the cube root, but square it. Anything I square is positive. So it's positive over here, positive over here. So this guy is actually always increasing from negative infinity to infinity. And then if I do f of 2 to find the actual point, it's not actually a max or a min, it's just a vertical tangent. F of 2 is 2 minus 0 to the 1/3 minus 4. Sorry, 2 minus 2 to the 1/3, which is 0 minus 4, so negative 4. So we have a vertical tangent at a 2, negative 4, if I were to graph it. Now the second thing I'm going to do is the second derivative. I suggest you go back to this one here, because again the 1 didn't do anything. The 1/3 x minus 2 to the negative 2/3. Drop that power down now. It's negative 2/9 x minus 2 to the 5/3, negative 5/3 times 1, which is just this. So now we get f double prime of x is negative 2 over 9x minus 2 to the 5/3. Okay, now again what happens is we get the same issue as before. I can't make the numerator 0 because it's always negative 2, but I can make the denominator 0 at x equals 0. And so I do have a concavity to check out here at, not 0, at 2. Okay. And now things are a little different. When I plug, since this is an odd power now, if I plug a negative in, if I get negative in here, it's going to stay negative, and that happens. Anything less than 2 gives me negative in here. So what ends up happening is I get the negative 2 on top, and then the negative in the denominator. That's actually positive. And then I get anything here, whenever it's bigger than 2, I get a positive in the denominator. So I get negative over a positive. That stays negative. So I did have an inflection point actually at 2, which we already know what the x value was. It was 2, 4. Or sorry, 2, negative 4. And then concave up from negative infinity to 2, concave down from 2 to infinity. Okay. And this one really wouldn't have been all that bad to graph, but it just, what happens is your 0 is at like 66, and just, it was a pain in the neck, so I just said, let's not mess with it. Okay. All right then, next one we are going to graph. This one will probably take us a little bit longer because it's a rational function, and rational functions always take a little longer to do, because we have to do all of our asymptotes. Okay. So number 726, we have 3x, we have n of x equals 3x squared over x squared minus 9. Okay. Domain, first thing, that's A. Domain is that x cannot be positive or negative 3. That would give either one of those zeros. So there's two domain issues. B, the zeros, set 3x squared equal to 0. That gives us x equals 0. So our zeros are 0, 0. And then it also takes care of our y-intercept. Our y-intercept is 0, 0 when you plug 0 in for x. Now I got to start doing our increasing decreasing business, so I have to do my first derivative. Well, I'm going to have to do the quotient rule for that. So the derivative of the numerator, 6x, denominator leave it alone, x squared minus 9, minus the numerator, left alone, times the derivative of the denominator, which is 2x, all over the denominator squared. Okay. Now, at this point here, what I have to do is I do have to simplify the numerator. Okay. When I distribute that, I get 6x cubed minus 54x. Okay. And this is actually minus 6x cubed, which luckily for us, and a lot of times in these ones that we've been doing, this cancels off the x cubes. I get negative 54x over x squared minus 9 squared. Now, this has, I could set the numerator equal to 0 to make the fraction 0. That gives me x equals 0 as a critical number. And if I set the denominator equal to 0 to find the undefineds, my critical numbers are 3 and negative 3, but they don't fit in the domain. Sorry, it should be x can't equal, by the way. Just caught that. X can't equal 3 and negative 3. So the only critical number I have is 0. However, when I do my number line testing, I have to test around the negative 3 and 3 because the graph is broken up into 3 parts. Okay. So now when I plug a number in left of negative 3, like negative 5, something like that, negative times negative on top is positive. The denominator is going to be squared, so it's always positive. So that portion's increasing. It's positive there. Now when I plug a number between negative 3 and 0, like negative 1, negative times negative is positive. This is always positive in the denominator. So we're positive there. Then after 0, I plug a positive in. That's negative on top over positive. So negative. And then once I get past 3, I plug a positive in. It's negative on top over positive. It's negative. So I have a max, which actually is a relative max, at x equals 0 of 0. We've already found that point. That was 0, 0. And then I'm increasing from negative infinity to negative 3, and I have to break this up because the graph does break up by a vertical asymptote, and then from negative 3 to 0, decreasing from 0 to 3 and 3 to infinity. Okay. Now I'm going to jump to another sheet of paper because the second derivative is going to be a little bit more work, but we'll come back to that in a moment. So my first derivative was negative 54x over x squared minus 9 squared. Now my second derivative in double prime of x. Derivative of the numerator, negative 54, leave the denominator alone, x squared minus 9 squared, minus numerator left alone, times the derivative of the denominator. Well, that's going to be a product rule, or sorry, a chain rule of 2, bring that down to the front, x squared minus 9, subtract 1 from the exponent, 1, and then derivative of the inside, which in this case is 2x. And then we leave the denominator alone. And then what really happens is this. I have a negative 54 and 1 x squared minus 9 in every term. So I'm going to take that out. In double prime of x, take out the negative 54, take out the x squared minus 9 to the first. That leaves me with then here in the first group just one of these. In the second group, it's minus x. This is gone. 2 times 2x. Over the denominator, which these guys multiply together, so I get x squared minus 9 actually to the fourth. Okay. And now two more things are going to happen. First of all, this is minus, minus 2x times 2 times x, so that's going to be minus 4x squared. And then here I can cancel out one of those guys and make that x squared minus 9 cubed. And then when I have this be minus 4x squared and 3x squared, that's negative 3x squared minus 9 over x squared minus 9 cubed. And you might catch one more thing. If I think of taking out a negative 3 on top, which I can do, I get x squared plus 3 all over x squared minus 9 cubed. And then the negative here and the negative here cancel. 54 times 3 is 150 plus 12, so 162. And hopefully you'll catch then, and I know this is again a lot of work. Okay. The 162 times x squared plus 3 over x squared minus 9 cubed. Hey, we have a problem. X squared plus 3 can't solve for 0. That means I don't have any inflection points. So no inflection points. Now, to check my concavity then though, I still have to check between negative 3 and 3 in the second derivative. But the nice thing is, no matter what happens on the top now, that'll always be positive because positive 162 times something squared plus 3, that stays positive. It's the denominator that'll be an issue. So when I take a negative and square it bigger than 3, like 5, negative 5, it's 25 minus 9. Oh, it's positive, cube of positive, it's positive. So it's concave up from negative 3, from infinity to negative infinity to negative 3. Now I take a number between negative 3 and 3, like let's say 0. Well, again, positive on top, but 0 minus 9 is negative. Cube that stays negative. Negative there, concave down between negative 3 and 3. And then when I plug a positive number in bigger than 3, it kind of mirrors over there, I get positive. Okay. So no inflection points, but concave up from negative infinity to negative 3 and from 3 to infinity. Concave down from negative 3 to 3. Now, the very last thing I have to do before I graph this, which was not included on this worksheet, but we needed to do because it's something we've been doing since chapter 1, is we need to check our asymptotes. So our original function was n of x equals 3x squared over x squared minus 9. So the first thing I have to do is check the limit as x approaches infinity of 3x squared over x squared minus 9. Now our trick for that is to divide everything by x squared. Okay. What that leaves us with is the limit as x approaches infinity of 3 over 1 minus 9 over x squared. Hey, as I throw infinity in, 9 over infinity goes to 0. We get 3. So to the right, our asymptote is y equals 3. And then when we do the limit as x approaches negative infinity, it's just the same thing. But we still have to go through the trouble of doing this because, even though we haven't seen it for a while, there were some functions that had different asymptotes to the right and to the left. This gets us 3 over 1 limit as x approaches negative infinity. 3 over 1 minus 9 over x squared. Again, this goes to 0. 3 over 1 equals 3. So we only have one horizontal asymptote, y equals 3. Okay. Now the next thing I have to do then is check the vertical asymptotes. So this is the horizontal. Here's the vertical. Okay. Limit as x approaches 3 from the left. Limit as, put this in the screen there, Mr. Moore, as x approaches 3 from the right of 3x squared over x squared minus 9. 3x squared over x squared minus 9. Okay, so on top, I can really just think of this as, and I like to put approximate because it's not really equal to, but it's approximately equal to me plugging 3 in. Just a little bit smaller than 3. Well, it doesn't matter. I'm going to square it and then multiply by 3, so I'm going to get 27 about. On the bottom, though, a number a little bit less than 3 is like, it's going to be, when I square it, a little bit less than 9. So minus 9 is at negative, quote unquote, negative 0. This guy blows up to negative infinity then. Now I do the same thing over here. I get 27 on top, and then I'll get a number bigger than 3. So when I square that, it's bigger than 9, so quote unquote positive 0, and that gives me then positive infinity. Okay. Now I'll do the limit as x approaches negative 3 from the left of 3x squared over x squared minus 9, and the limit as x approaches negative 3 from the right as of 3x squared over x squared minus 9. Okay. Now, when I think about plugging negative 3 in, again, square it, stays positive. Again, that's really like 27 on both of those on top. But now left of negative 3 is like negative 3.1. So that's actually bigger than 3 when it's bigger than 3 for an absolute value. So when I square it, it's bigger than 9, quote unquote positive 0. That blows up to positive infinity. When I go to the right of negative 3, that's like negative 2.9. So that's going to be less than 9 when I square it. So that's that quote unquote negative 0, negative infinity. Okay. And now I'm ready to graph because I've done everything for this graph that I can do. And even though I'm taking my time, might feel like I'm flying through it, but I am taking my time, and I've done none of this on a calculator. None of it. That's the point and the power of this work. So horizontal line, horizontal line. Okay. I have horizontal asymptotes, or sorry, vertical asymptotes at x equals positive 3, x equals negative 3. I had a horizontal asymptote at y equals 3. Okay. Now, as far as points are concerned, I only had one point. 0, 0. That was it. 0, 0 was the only point we actually found of anything that was of substance. So I'm going to do this in green or red to make it stand out. So 0, 0 is right here. Okay. But I did know that it was increasing from negative infinity to negative 3, and then from negative 3 to 0. And I knew it was decreasing from 0 to 3 and from 3 to infinity. And then I also knew it was concave up from negative infinity to 3 and from 3 to infinity, and then concave down from negative 3 to 3. Okay. So what that means is over here the graph had to be going towards 3 from the left and then up to positive infinity, because that was the behavior. If I look at negative 3 from the left, it was to positive infinity. So the graph is just, for our case, just doing something like this. If you want more accuracy, you just pick some points and plug it in. Then it's increasing from this guy to 0 and concave down the whole time and then decreasing. So again, just something like this. And I'm not too picky about your accuracy because, as you can see, I am a terrible artist and terrible drawer, but just something that gives the general behavior. And it was negative infinity for both these guys for asymptotes. And then up here, it's just basically the mirror image of the other asymptote. So there we go. Okay. Now, for the last one for this part here, 727. Okay, sorry, 727. We have f of x equals x cubed e to the x. So again, extrema for this. Well, the first thing I need to know is domain. And I can plug anything I want in for an exponent and anything I can cube. So domain's all reals. Now, first derivative for this function is going to be a product rule of 3x squared times e to the x plus x cubed times the derivative of e to the x, which is e to the x. Now to find those zeros, I suggest you factor out the e to the x and an x squared. That leaves you with 3 plus x. So we're going to get two zeros then for this. When x is 0 and when x is negative 3. Okay. Oops, put negative 3 on the left here, put 0 on the right. Okay. And now, my computer screen keeps going to sleep. So, and now I get numbers to test. Well, here's the deal. No matter what happens, for this guy, it's going to be positive. I'm going to square it. E to any power is positive, so I'm going to square that. So really what I need to do then is figure out what happens when I plug a negative 3 in. Well, left of negative 3, gives me negative. After negative 3 gives me positive as well. So what I actually have going on here is I have a minimum at x equals negative 3. This is just a horizontal tangent there. And I'll plug negative 3 in to see what I get. F of negative 3 is negative 3 cubed, e to the negative third. Well, that's negative 27 over e cubed then. And if this were your test, you'd be done now, because I didn't make you find inflection for this. And if you look at my work, it took me all of 32 minutes, 34 minutes. So, and that's me talking, me writing everything, every single step out, me, explaining, doing all the different drawing stuff like that. If I'm not talking and I know what I'm doing, these don't take that long to do. And I, again, didn't use a calculator on any of it. Now, the last thing we're going to find then are the inflection points. So this is where this one gets a little ugly at. I'm going to go actually to make this easiest on myself. Make this 3x squared plus x cubed and do a product rule with it for this. So for the second derivative of x, e to the x stays e to the x, leave that as 3x squared plus x cubed. Okay. Now the e to the x stays the same. Derivative of this guy is 6x plus 3x squared. Okay. What I can do then is I can take out an e to the x and an x. And that gives me 3x plus x squared plus 6 plus 3x. This simplifies to be x squared plus 6x plus 6. And this is where this really becomes a pain in the neck. I get x equals 0. That's easy enough to mess with. Oh shoot, I'm sorry, I'm running out of screen. This guy here, x squared plus 6x plus 6, that's going to be a quadratic formula problem because it doesn't factor. There's something that multiplies to 6 that adds to 6. So x equals the opposite of b, plus or minus square root of b squared minus 4ac. Well, that's 36 minus 24, so it's 12, over 2a, which is 2. X then becomes negative 6 plus or minus 2 root 3 over 2, or more importantly, it's negative 3 plus or minus root 3 when I divide all the 2's out, which is negative 3 plus root 3, negative 3 minus root 3. And as I go with my number line here, then to find inflection points, negative 3 minus root 3 is the smallest, then negative 3 plus root 3, and then 0. So if I go back to this, Okay, if I go back to this, it's actually kind of strange. What happens is this is always positive, this is always positive, so this guy is our real workhorse. So this is negative, this is negative, this is negative, this is positive. So our change of inflection is at 0, 0. No, Mr. Moyer, you silly goose. This isn't always positive because that 6x can change things. Ah, dang it. Let's see here. Ooh, I'd have to get an approximation for that, wouldn't I? Yeah, I would. So what I get for trying to just make one up on the fly and work it out. All right, I was trying to do this out of calculator, but I have to break down, use my calculator. Okay. So the e to the x is always positive. So what I really am concerned with is what happens with negative 3 minus root 3. That's going to be the x, and then times parentheses negative 3 minus. Oh, I got to pick a number. Oh gosh, what's? This is why I would never make you do this on a test. This is way too much work. That's negative 4.7. Let's say, and then this guy here is negative 1.26. Yeah, because this would be negative here. Ugh. So this will be negative. And then I got to think of a number like negative 5. So negative 5 would be 25 minus 30 plus 6. So 25 minus 30, that's 31. So that's positive. So negative times positive, that's negative over here. Now when I get into here, a number like negative 2 is 4 minus 12 plus 6, it's negative 2. Okay, so this is positive here. And then it's negative. Okay, yeah. So there are actually inflection points at x equals negative 3 minus root 3, negative 3 plus root 3, and then 0. And then it's concave up. I'm not going to bother to find the y values. It's not that important. It's going to be some weird, like this quantity cubed times e to that quantity. It's just, I don't even care. Concave up from negative 3 minus root 3 to negative 3 plus root 3, and then from 0 to infinity. And then concave down from negative infinity to negative 3 minus root 3, and then from negative 3 plus root 3 to 0. Okay. So there we go. Okay, now we can get out of these kind of stranger problems, or the weird graph ones, and start jumping to some of the kind of more interesting ones. All right, so number 30 says sketch a graph where whose derivatives satisfy the properties of the given table. So what we're given is x and f prime of x. So go to my graph paper. Here's what I know. Here's what I know. I know that from negative infinity to negative 1, the first derivative is positive. So it's increasing here. Okay. Then from negative 1 to negative 1, the derivative is 0. So this is a horizontal. And then from negative 1 to 1, it's decreasing. And then at 1, it's horizontal. And then it's still decreasing. So this is not a minimum here. This is just it's going to go something like that. And then here it gets to 0, so it's horizontal, and then it's increasing at 3. Now it doesn't say what the y values are, so I get to make those up. But I have to look at negative 1, 1, and 3. So in fact, what I'm going to do is I'm going to just, and it's positive before negative 1. So I'm going to say, okay, you're just going to go up until you get to this. Then it starts to hit 0 and then starts to go down. So okay, so turn, you go down, and then at negative 1, horizontal for a brief moment, and then it's negative again, so you still go down. So I'm going to turn down, and then at 3 you're horizontal again. but now you're going to start going up. So that's a possible graph for this. Again, it could be anywhere. There could be all kinds of crazy stuff, but this is the one that I kind of came up with on the fly. So again, decreasing, horizontal, decreasing, horizontal, switch up. Okay. Now 731. 731. Okay. I'm going to fold my paper over so I can just see that. So suppose f has a continuous derivative whose values are given in the following table. So at 0 the derivative is 5, 1 it's 2, 2 it's 1, 3 it's negative 2, 4 it's negative 5, 5 it's negative 3, 6 is negative 1, 7 is 2, 8 is 3, 9 is 1, 10 is negative 1. Alright, so estimate the critical numbers. Okay, so in order for it to be a critical number, that means that the first derivative has to be 0. Now if we're told that this is has a continuous derivative, that means by the intermediate value theorem, here and here it had to go from positive to negative. Here and here had to go from negative to positive. Here and here had to go from positive to negative. So I know my zeros are on the intervals of 2 and 3 for x, because again I'm talking about the x values, between 6 and 7, and between 9 and 10. Those are the three intervals I must have a 0 at. And then looking at their values, it went from positive to negative. That's increasing to decreasing, so this is a max. This one here went from negative to positive, so decreasing to increasing, so a min. And this went from positive to negative, so it's also a max. Now one more thing I want to make note of too is this. I could also roughly determine concavity, because concavity is the rate of change of the increase and decrease. So this guy went negative 3, negative 1, positive 3, negative 3, positive 2, positive 2, positive 2, positive 1, negative 2, negative 2. And I know that doesn't really show up that well. I'll zoom in a little better on it. And then try to autofocus it. Yeah, there we go. It's hopefully better for you. So here from 0 to 2, we have negative second derivatives because that's the slope of the first derivative, or it's the change of the first derivative. Oh, sorry, that's so sloppy. Ugh. Okay, there's f double prime x. So we could say from here to here, our idea is our second derivative is negative. So it means we think it's concave down roughly from 0 to 2. Then it's positive from 2 to 3, so we'd say it's concave up from 2 to 3. And then from 3 to 4, it's a negative change again, so it's concave down. And then from 4 to 8, these are all positive changes. So from 4 to 8, we would argue it's probably concave up. And then after from 9 to 10, we'd say it's negative, so it's 9 to 10, it's concave down. Sorry, I got this there. Can fit it all kind of in there nicely. There we go. So I didn't ask you for concavity, didn't say that at all, but we can sort out our concavity from a table as well, so don't forget that, by looking at the differences for the first derivative if the x's are consistent, so it's the same distances. Okay, now on the back, 733. 733. This one is a whole lot of paying attention to what you're being asked. 733 is a whole lot of paying attention to what the problem is asking. Okay. And what they've told you have. 733 says the figure below shows the graph of g prime. That means this is the derivative, not the function. So the first one says, what are the x values for relative minimum and maximums? This is not a maximum. A maximum is where the derivative is 0. So our derivatives are 0 at between negative 2 and negative 3, at 0, at 2, and at 4. Those are our possible max and mins. So the question is, what type are they? Well, this guy here would be a min, because I went from negative values of the derivative to positive values. So from negative to positive. So that means I must have gone downwards. This guy here went from positive values to negative values for the derivative, so this is a maximum. This guy here went from negative values to positive values, so this is a minimum. And then right here we don't know, it looks like it'd be a max, but it could be turning back up. We really can't call it anything. Sorry, I shouldn't have considered that one of them, because it's going to stop. Although it is a close. Well, I could say this is an absolute max or min. I have to look at this, but this would be a possible max because it is on a closed interval. And this guy here would be a min because he's on a closed interval. Okay, so we could kind of argue that, but that's only really if we have the function we want to do that. With the graph, we just want to ignore it. B, determine the values of x, which is concave down and concave up, justify your answer. Well, if I want to look at concavity, what I'm looking for is in the first derivative, where is it increasing and decreasing at? Well, it's increasing from -3 to this point here, which looks like -1.5. So it's concave up from -3 to -1.5. Concave down from -1.5 to 1. And then it's concave up from -1.5 to 3. And then it goes down again from 3 to 4. Okay. Now, here is probably what might be the hardest part for this one. You are given this information, and you must create a graph now. I'm going to just kind of zoom out a little bit. Actually, I'll do this. Make this Sharpie. I've got -3, 3, and 4, 6. So I need probably pretty good. Oops. I don't have any other graph paper printed out. I don't want to redo this. That's why I use pencil, not marker or pen. Either way, I have 2 points they've given me on part C. It says G -3 is 3. So G of -3 is 3. And G of 4 is 6. G of 4 is 6. Okay. Now, I know I have a minimum at -2.5. Okay. So like -2.5, there's a min. I'm just going to put a min there. Okay. I know I have a max at 0. So I'll just make 0 some point there. I have to do this thing. Sorry, it's going to bug me to do that too much. Okay, so let me start this over. I'll just do, I'll do the x-axis in black, x, y-axis in black. Make it stand out a bit. But I'll do the graph in red. So I'll just start that over again. So I know I have at -3, the point 4, -3 is 3, -3 comma 3. And then I know at 4 I have 6. But I know I have a minimum at x equals -1, or min at x equals -2.5, and at x equals 2. Okay. Max at x equals 0, and that's it. Yeah, that's the only max I've got. I'm increasing from -2.5 to 0, and from 2 to 4, decreasing from -3 to -2.5, from 0 to 2. Okay. Concave up from -3 to -1, and from -1 to 3. Oh, it's -1.5, isn't it? Yeah, it wasn't -1. It was -1.5. We said, and then from +1 to 3. I think I messed up my points there. Yeah, I think I said -1.5 here, didn't I? That should have been, sorry. I was just Positive 1 to 3. Positive 1 to 3. Some of you are probably freaking out at me, and I'm sorry. Positive 1 to 3. And then concave, dang it, concave down from negative 1.5 to 1, and then from 3 to 4. Okay, so here's the deal. I need to create some max and min points, basically. I need to create a min at negative 2.5, so I'm just going to make a point. Negative 2.5, you get a min. And then a max at 0, so let's just throw the max up here. I like 0, 5. And then I have another min at x equals 2, so make like 2, 2. And then I know it's concave up from here until 1.5. So negative 1.5 would make a point where if this is the minimum, it's got to be above, it's got to be between these two here where I switch concavities. I'm just going to throw like right here. So concave down, or sorry, concave up. There I switch my concavity. Okay. And then I'm concave down until 1. So somewhere at 1 I have to switch concavity again, so I'm going to throw a point between those two. Then I can go concave down and now switch concave up. And then I'm concave down again at 3, so I'm just going to throw a point between these two here where x is 3 that I'm increasing, but switch my concavity there. So it's not perfect, but it's just got to, I mean, it's not exact, and there's not one answer only, but this one gets to all the behaviors that's given by our graph. It would have all those things. Okay. Now, the last 3 problems on your worksheet, are linear approximation problems. So from section 3.1. So number three, you are supposed to create a linear approximation using f of x equals the square root of 2x plus 9, x naught is 0, and you're doing the square root of 8.8. Okay, now, all linear approximation is find the equation of a tangent line given a certain x value, and then using that tangent line to approximate another value. So, in order to, the formula the book uses for this is just fancy point slope form. Again, f of x is y, so the line of x is the y naught plus the derivative at x naught. Well, that's your slope at x naught times x minus your x naught. It's just point slope form, where that modified point slope form where they put the y in front. So the first thing we do is we find f of, we already know our x is 0. Well, let's find f of 0. F of 0 is 3. Okay, so L of x is 3 plus, I'll find slope in a minute, then x minus 0. Now in order to find the slope, I've got to find the derivative at that point. So find f prime of x. Well, this is really, f of x is really 2x plus 9 to the 1/2 power. So drop the 1/2 to the front, leave the inside alone, subtract 1 from the exponent, multiply by the derivative of the inside, which is 2. 1/2 and 2 cancel. I get f prime of x is 1 over, because this moves to the denominator now, 2x plus 9 to the 1/2 power. We'll now find f prime of 3, or sorry, f prime of 0, because that's what we have as our seed value is 0 right there. 1 over 0 plus 9 to the 1/2 is 1 over 9 to the 1/2, which is 1 over 3. Get my computer screen's going to sleep, because every 15 minutes I think is what it's set for. So 1/3. Okay, there's our slope. So there's our linear approximation, 3 plus 1/3 x minus 0. Now, in order to actually use that, I got to figure out what to plug in for x to get 8.8 out of this guy. So that's where we set the square root of 8.8 equal to the square root of 2x plus 9. So square both sides. 8.8 is 2x plus 9. Subtract 9, negative 0.2 is 2x. Divide by 2, negative 0.1 equals x. That's what I'm going to plug in to this line here to approximate the square root of 8.8, because based off of this equation, negative 1.1 would get us 8.8 on the inside. So L of negative 0.1 is 3 plus 1/3 times negative 0.1 minus 0. Well, that's really just negative 1/10 on the inside. So I get then 3 plus negative 1/30, which is 2 and 29/30. So the square root of 8.8 is approximately 2 and 29/30. And if I want to check to see how good that approximation is, I get out my graphing calculator. Second square root of 8.8 is 2.9664 whatever, and then 2 plus 29/30, because that's how we do our mixed numbers with this guy. 2.96 repeating. So it's pretty darn close. We get up to the we're the same until we get to the 10,000ths. So that's how we do our linear approximations. Now the other one, just more practice. Number 4, 2 over x, and doing then 2 over 0.99. Now this one you actually could divide out, so this isn't a big deal, but just to kind of get a little bit something else, a little different flavor. So f of x equals 2 over x, x naught equals 1, and I'm going to do 2 over 0.99. So first of all, f of 1 is 2 over 1, which is 2. So my ordered pair is 1, 2. So L of x is 2 plus the slope times x minus 1. I don't need this anymore, so I'll put you away for a bit. Next thing I have to do then is I have to figure out what's the slope for my tangent line. Well, go back and do the derivative of this. The easiest way to do the derivative of this guy is to say f of x is 2 times x and negative 1. You can see my endurance is waning here. It's an hour in and I'm really getting sloppy. And this is really having a tough time focusing. So 2x to negative 1, so f prime of x is going to be negative 2x to the negative 2, which is really negative 2 over x squared. So when I do f of 1 then, I get negative 2 over 1 squared, which is just simply negative 2. So my slope then is negative 2. Now there's my approximate line. So now I want to do 2 over 0.99. Well, if I set 2 over x equal to 2 over 0.99, it's pretty obvious x has to be 0.99. So L of x is 2 plus negative 2 times 0.99 minus 1. Well, that's negative 0.01. So that gives me then that L of x is 2 plus positive, because the negatives cancel, 0.02, 2.02. There's our approximation. And then if I want to see what this is a, a better approximation, 2 divided by 0.99. 2.020202 repeating. So again, not too far off. And then the last problem from the homework assignment. Last problem from the homework assignment. Number 11. An animation director. Let's throw that out there so we can kind of look at it, and I'll do my work on other paper. I don't need you right now, so we'll come back to you later. Okay. An animation director enters the position f of t of a character's head after t frames of a movie is given in the table. All right. If the computer software uses interpolation to determine the intermediate positions, determine the position of the head at frame numbers 208 and 232. Okay, now 208 is between here and 232 is between here. Again, all we're doing is finding the equation of a tangent line. The difference is I can't find the exact slope at that point because I don't have a function, so I have to approximate slope. So for 208, I will use these 2 points. Okay. So my approximate derivative is going to be 142 minus 128 over 220 minus 200, which gives me then 14 over 20, which is 7 over 10. Okay. Now there's my slope. Now I just pick one of those x and y's. I'm going to go with 128 and 200 because 200 is a nice easy number. There we go. Oh, sorry, I got that backwards. This should be 128 because that's the f of t. That should be 200. L of x is going to bug me. 128 plus 7 over 10 times x minus 200. And then for part A, then plug in 208. That's really 8. And then this would be 56 over 10, so 5.6. So I expect it to be at a position of 133.6 at 208 frames. And then for part B, you do the same thing, but this time we will use, since we're going to do 232, we will do those two guys for the slope for part B. So (136 minus 142) over 240 minus 220 gives me negative 6 over 20, which is negative 3/10. Okay. Now, just pick an x and y value. So I don't know. Let's do 136 plus negative 3/10 times x minus 240. Okay, so I chose to use this point here. And then plug in 232 because that's what I'm trying to figure out. Is it 232? (232 minus 240 is negative 8. That actually becomes plus 24 over 10, which is 2.4. Whoops, sorry, 138.4. Okay. Yeah, there we go. There's the entire homework assignment. Okay. What I suggest you also do, okay, over the weekend, while you're reviewing stuff, we had in section 3.4, no, here we go, 3.2 and 3.4, we had these AP examples that I went over in class, okay, we talked about. I suggest you look through these again. Okay, I don't think I can legally go over these online because they're from practice AP tests. But look through them. I can talk to you about them before or after class sometime or something like that. But some of you guys, you missed problems exactly like this one here on that pretest, and there's no reason to miss that. That's just purely not paying attention to what you're supposed to do. Same thing here, giving you, a function to find max and min or in concavity or whatever it was. All kinds of stuff, just little simple things missed. Table values, graphing, things like that. So yeah, go through these problems here and or come in and see me and we can talk about them. Okay, thanks. Oops, there we go.